A ball falls straight down through the air under the influence of gravity. There is a retarding force F on the ball with magnitude given by F equals bv, where v is the speed of the ball and b is a positive constant. What is the ball's terminal velocity? At what time is the terminal velocity obtained? So if we draw a free body diagram of this ball when it is at terminal velocity, it's going to have the retarding force F, that is drag, that's preventing it from accelerating, as well as the force of gravity, or mg, its weight. And if we say the downward direction to be the positive x-axis, then we can say that mg minus the force F must be equal to the mass times the acceleration of the object, which is going to be 0 at terminal velocity. So at terminal velocity, the object stops accelerating. So we also know that the force is equal to a positive constant b times the velocity v. So mg minus bv is equal to 0. So therefore, bv is equal to mg. And this v is the terminal velocity, vt. So the terminal velocity is equal to mg, or the weight of the object, divided by b, which is the positive constant. So that's our first part of the problem done. So the terminal velocity is equal to mg over b. Now it asks us for the time of the terminal velocity. So if you remember from our equation, we can say that mg minus bv is equal to ma. But this time, we can replace a with dv dt, since the acceleration is the rate of change of velocity with respect to time. So mg minus bv is equal to m times the derivative of the velocity with respect to time. And from here, we can separate our variables. So say that dt is equal to m dv divided by mg minus bv. And that is simply separation of variables. From there, we can integrate the left side from 0 to the time t dt, which is the summation of all of the infinitesimally small dt's. And that is going to be equal to the integral from 0 to v of this m divided by mg minus bv dv. So the left side simply becomes t, since you're adding up all of the tiny little t's. And then we can move m outside because it's a constant. And this becomes the integral from 0 to v of 1 divided by mg minus bv. And this is dv here. And this becomes, let's see, from here, we can use u substitution and replace this with u. So if we let u equals mg minus bv, then du is going to be equal to minus b dv. And this is a constant. Negative b is a constant. So can replace t equals m, and this is actually minus m over b, since we're dividing it by minus b if we want to multiply the inside by minus b. And this becomes the integral of 1 over u. Remember, we substituted u in here, du. So the time simply becomes minus m over b times the natural log of u. So if I make some more space here, let's get rid of all of this. And if we remember, it's m over b. U is simply mg minus bv. And there's not enough space here. I'm going to try to write this slightly smaller. Ln of mg minus bv. And we're evaluating this from 0 to v, if you remember. So this becomes minus m over b times the natural log of mg minus bv minus the natural log of mg. There's barely enough space here, but if I try to close this, I probably should have removed the arrow here, actually. Yeah, here. Actually, sorry about this. I'm going to rewrite it. So if I remove this, this becomes t equals minus m over b times the natural log of mg minus bv minus the natural log of mg. And all we did this was evaluate the values between 0 and v. So we plugged in v for the first part and subtracted the second part where we plugged in 0 for v. And we're left with this over here. So we have this over here. But if you remember, this can be simplified to the natural log of mg minus bv divided by mg. This is simply by the mathematical logarithm properties. And that is equal to t. So here we need to solve for the velocity, as we can use a limit to figure it out. So right now this equation gives us the time in terms of the velocity. So, but we need to figure out what the time is when the velocity is equal to this terminal velocity here. So we need to solve for the time when this velocity is at the terminal velocity. So we can replace this saying that e2, hold on, so we can multiply both sides by b first, separate out the natural log, g minus bv divided by mg. That is equal to negative bt divided by m. We just got rid of these constants here. And then we can get rid of the logarithm to get mg minus bv over mg equals e to the minus bt divided by m. This is because the natural log is basically saying that e to this power here is equal to this. So the natural log, this really means the logarithm of e. If I write this here, that's equal to minus bt over m. Okay, I'm gonna simplify this a little bit so that I don't have to write much. If you have like the log of 2 to have like 16, that equals 4. Then this is basically saying that 2 to the 4th power is equal to 16. This is the same thing here. The natural log has e as its base. So e to this power is equal to this. And that is basically where this equation comes from. So that is our equation there. Then we need to continue solving for bv. So after that, we can bring out this. So multiply both sides by m. mg minus bv is equal to mg e to the negative bt over m. And so negative bv is equal to mg e to the minus bt divided by m minus mg. So v is equal to mg minus mg times e to the power of minus bt over m divided by b. That's our equation after we simplify that for the velocity. So you can say that the velocity is equal to mg times 1 minus e to the negative bt over m divided by b. And this would be our equation for the velocity. Now, let's think about what happens as the velocity approaches to the terminal velocity, or when the velocity approaches this mg over b. I will rewrite this to make it more familiar. I can rewrite this. So velocity equals mg divided by b times 1 minus e to the negative bt over m. What will happen as the velocity approaches this b value? Or rather, we should think about what happens if the time approaches infinity. So as the time approaches infinity, this part becomes negligible. So when the time is much greater than the time of flight. Let's just say that the time is very big and is approaching infinity. Then this e will become negligible. It's almost close to zero because it has a negative exponent. So basically it's 1 over e to whatever this value gives us. So as t becomes very big, the fraction becomes, the denominator of this fraction becomes very big. If you think about it, this really is just 1 over e to the bt over m. As t approaches infinity, this will approach 0. So really, you can say that when the time approaches infinity, velocity is going to approach the terminal velocity, which is equal to mg over b. So when this asks what time is the terminal velocity obtained, this terminal velocity is really obtained as the time approaches infinity. And that is how you would solve this problem here.